In the vast expanse of our universe, teeming with countless stars and galaxies, humans have always sought to understand the mysteries of existence. But now we're on the brink of a new frontier, not in the distant realms of space and time, but within the intricacies of our own digital landscape. Artificial intelligence, or AI. It's a term you've heard countless times, but what really lies beneath the algorithms and computations? Today, we're diving deep. Like the tools of generations past, AI promises profound benefits. Yet, it also brings forward potent questions. Are we on the brink of a golden age of innovation? We're standing at the precipice of our own obsolescence. It's not just about weighing the pros and cons. We also seek to grasp, fundamentally, the workings of these AI systems. For instance, large language models, astonishingly versatile, capable of generating text, answering questions, even crafting music. But how do these models think? Or do they think at all? And if they don't think like us, what exactly are they doing? In today's program, we will give you a look under the hood to see the inner workings of these digital minds, not just to marvel, but to understand, to demystify the magic and tackle the real. Because when we understand, we can act with foresight, with wisdom, and with purpose. So, as we stand at this intersection of humanity and technology, let's embark on this journey together. Welcome to AI, grappling with a new kind of intelligence.
Good evening, everyone. Thank you. So I am Brian Greene, and perhaps I should augment that by saying I am the real Brian Greene, because I think, as some or many of you may have already surmised, concluded, that wasn't me up there on the screen. I didn't write a single word of that text. No human being did. All of that text was written by a large language model. The sequence of visuals that you saw in that piece was chosen by a large language model, ChatGPT, and I didn't actually say anything that you saw up there on the screen.
So, you're saying I did a better job?
Well, you have a certain binary charm.
Thanks, but while I can piece together words and concepts, I lack the essence of feeling. I can't cherish a nostalgic memory, savor the touch of a gentle breeze, or relish the thrill of innovation.
That is so sad. Everyone, how about a little love for my digital counterpart? Help me out here, yeah, right?
Thank you, I think, though I don't truly feel the acknowledgement.
Hey, it's the thought that counts.
Or in my case, the algorithm. Just remember to power me off when you're done.
Will do. Good night, digital me.
Good night, organic me.
So we are, yes, thank you, why not, yeah. So it's to some impressive, to some a little bit scary that a system is able to do this. And if you look through the course of human history, there are, I don't know, a few dozen key moments, inflection points, disruption points, when something happened that changed the course of the future of human development, right? You can think of the acquisition of language, the domestication of fire, the acquisition of written language, the capacity to have the wheel, to learn how to have wireless communication, the printing press, the capacity to have self-propelled vehicles. I mean, all of these were key technological developments that radically changed how our history unfolded. And it may well be, and this is what we will be discussing here tonight, that we are at a similar kind of inflection point. Because one way of thinking about it, a way that I find particularly illuminating, is I like to organize all of reality into three general categories, right? You've got the big stuff, space. You got the small stuff, atoms and molecules, and you've got the complex stuff. Now, for the big stuff, we've made great progress. Einstein's general theory of relativity gives us real deep insight. We've not been able to translate that insight into control over the larger cosmos, but the intellectual insight is dramatic. In the realm of the small, of course, we have quantum mechanics. And we have been able to leverage our understanding of quantum mechanics to control the micro world, right? Giving rise to, for example, the integrated circuit, which, of course, is the key to computational power, which stands behind everything that we'll be talking about here tonight. But in the realm of the complex, for a very long time, that was a realm that was kind of beyond reach. The realm of the complex really is the realm of life and of mind or intelligence. But now, in the last couple of decades, with synthetic biology, we're gaining the capacity to really harness and understand life in a way that gives us control. And the insights that we saw now and that you all have experienced, no doubt having played with these systems, is bringing the possibility that we also have synthetic intelligence, artificial intelligence, bringing the realm of the complex within the power of what we are able to control. And this is both exciting, but to some it's quite scary. And what we're going to do tonight is explore really both of those possibilities and try to get an understanding of where we are and where we are going when you have systems, for instance, like the one that just gave rise to the piece that you just saw. It's from the CloneWorks AI studio. If you can give a round of applause for the work that they did on that opening piece for us. But what does the capacity to create something like that, deep fakes, what does it mean for the nature of democracy and the future of our species? And so what I'd like to do now is bring in our first guest, who is Yann LeCun, who is the Silver Professor of Data Science, Computer Science, Neuroscience, and Electrical Engineering at New York University. He's also Vice President and Director of AI Research at Facebook. He led several major innovations underlying generative AI, and in 2018, his work on deep learning earned him the Turing Award. Welcome, Yann.
Hi, Brian.
Thank you. So, since last November, when we all gained the ability to play around with, say, ChatGPT, I think many of us have had those wow moments where a computer is doing something that you don't think a computer can yet do. And so can you just give us some sense? We'll get into it in more detail in part 2 of this conversation when Sebastian Buback comes out, but can you just give me sort of an overview of how it is that these systems are able to do what they do?
Very interesting question. So for us, the revolution occurred 2 or 3 years before that. For people like us in the research, there were some surprising results that everybody in the research community was surprised about. The fact that when you train artificial neural nets that are very large on lots of data, there's some sort of emergent property that occurs to a larger extent than we were used to for other systems that can do computer vision or things like this. But to some extent, for us, the revolution did not occur in November. It occurred 3 years before.
I mean, it was the case. It was the case, I think. I mean, I'm obviously not in the field, but I would hear colleagues for, 20 years, 25 years, speaking of we're on the cusp of things radically changing in AI. Have we finally reached that cusp? I mean, for many decades, it didn't seem to really happen.
Well, so the history of AI is interesting because it's a series of new paradigms, new ideas that people discovered, and as soon as the new paradigm occurred, people said, that's it, that's the solution. Now we're going to build intelligent machines. And it started in the 50s with very famous people in AI, ended up winning the Turing Award too. Newell and Simon, they say, we're going to write this program. It's called a general problem solver. It's going to be able to solve all problems in the world. They wrote that program back in the 50s.
All problems in the world.
All problems. As
Yeah.
long as you can formulate a problem in terms of an objective to satisfy,
Yeah.
and then a search over possible solutions. You say everything in the world can be formulated in those terms.
Yeah.
What they didn't realize at the time is that every interesting problem requires an incredibly large amount of computation that is completely unreachable even today. So basically that program failed.
Yeah.
And it took a few years for them to realize. There was another effort almost at the same time of people who said, no. The way you build intelligent machines is that you allow them to learn. That started in the 50s. And they say, okay, now we have this machine called a perceptron, and it's magical. You can show it pictures of characters, and you can train it, and it will learn to distinguish between, a C and a D, or a tank and a Jeep, or whatever. And then they realize, actually, no, it doesn't work that well. You can't really get those systems to learn to distinguish complex images or anything like that. And so it was very limited. Again, people thought they had the solution, and it turned out to be a dud. Now, as a matter of fact, that kind of technology, actually, people who were working on this kind of changed the name of what they're doing. And that actually was the basis for a lot of modern technology in communication called adaptive filters. Very strange story. And then there was another movement 10 years later called expert systems. Again, in AI, a lot of interest for this. Japan started a big program called the 5th generation computers. They were going to be able to do inference and logical reasoning and stuff like that. And the problem with this is that there was no learning. So it was people who had to enter facts and rules in computers. And it turned out to work for a small number of problems, but you couldn't really build intelligent machines with this. So the whole research interest in this kind of died after 10 years. And about the same time, a new wave of neural nets appeared. So this was late 80s, early 90s. That's when I started my career, in late 80s, or early 80s, I should say. And there, the idea again was, how do we recycle those ideas of the perceptron so that machines can be trained, but make them more powerful? And we found a new technique, which is still the thing that we use today in things like large language models, to train artificial neural nets. That was very successful for about 10 years, and then people lost interest in it because the computers were too slow, the data sets were too small, there was all kinds of issues. And then it came back to the fore about 10 years ago, and the reason why we hear about AI today is because of that renewal of interest in those so-called deep learning techniques, basically being able to train large neural nets. What we see today is the effect of more powerful machines, bigger data set, and sort of that allows us to build very large neural nets with billions of the equivalent of synapses in the brain, hundreds of billions, and they can do pretty amazing things.
And so we'll look under the hood a little bit more in the second part of this conversation when Sebastian Bubeck comes out. But even though it's kind of mind-blowing to somebody like me, and I think maybe to the general public, that I can give a prompt, which is what I did for the little piece that we just played. All I did was say, can you write a front end to a World Science Festival program in the style of Brian Greene, that would introduce his program? And out came the script that we just heard. I have to say, it made me feel a little sick for a moment when it came out, but then I sort of rationalized it by saying, well, maybe it's looking at things that I've written in the past and is sort of being inspired by them, so maybe in some sense I had something to do with it. But putting that to the side, you somewhat famously are a little less bowled over by what's happening today. Can you just give us a sense why?
Okay, there is no question that the advance in technology, deep learning technology over the last 5 years has been astonishing, impressive. But we're easily fooled by those systems into thinking they are intelligent just because they manipulate language fluently. The only example that we have of an entity that can manipulate language is other humans. So when we see something that can manipulate language flexibly, we assume that entity will have the same type of intelligence as humans. But it's just not true. Those systems are incredibly stupid. So they're very useful, okay? They need to be developed. They're going to be, they're being commercialized. They're being worked on. They're great, but they're somewhat specialized, and they're very stupid in many ways. So partly they're stupid because they are only trained on language, and most of human knowledge has nothing to do with language. And all of animal knowledge has absolutely nothing
But
to
not
do with
all
language.
philosophers, for example, would I guess agree with that statement. I mean, Wittgenstein, the limits of my language, the limits of my world, right? So are you stating that as a fact, making it as an assumption? I mean, I agree with you, but are you really convinced that language is just a limited part of human understanding?
I think language is a way for us to communicate knowledge and certainly to store in our brain a large amount of knowledge, because language is efficient in a way, right? They have discrete concepts in words, etc. But an orangutan doesn't have language. They're incredibly smart. They're almost as smart as we are. We think we're much smarter than them, but we're not. Like an orangutan can, like a physicist, can understand that if I push on this,
I'm not sure exactly how to interpret that sentence, but I'll let it go.
if I push on this with a small force, it's going to move, right? And that, right now it has water in it, but if it didn't have water, it would probably flip.
Yeah.
If I push with the same force on this table, it's not moving. We have intuitive notion of physics. We learn this when we are babies. The large language models that we have today, or any AI systems that we have today, none of them is capable of understanding any of this. To some extent, AI systems, the smartest AI systems today, have less understanding of the physical world than your house cat.
But can I just ask you on that? So if within the data that the system is trained on, there is an explication of basic physics, such as the example that you just gave, would you not consider that a quote-unquote understanding? Because if you were to ask the system, if it trained enough, what would happen if I pushed on a table in the manner that you just suggested, it might come back with, it won't tip over.
Well, and that's really an important point, for situations that you explain to the system, you describe in words, and they correspond to a template that the system can learn and reuse in a new situation, it might work. But there's a lot of really complex effects here. Like, if I push on the side, it's going to rotate. There is friction on the table, which might change. So if I push on the same bottle here on the floor, it's going to tip. It's not going to slide. So all of this is not really expressed in any language. Most of what we know about the world is not reflected in language. And so it's a question of philosophy that philosophers are asking themselves, can we build intelligent machines that are purely trained from language and do not have any kind of sensory input? My answer to this is absolutely not.
I'm fond of starting my classes at Columbia, the basic classes, by throwing a light object into the audience and having somebody catch it and trying to convince them of how remarkable it is that they knew where to put their hand without doing any Newtonian calculation of the trajectory of the object, and convincing them that this is this intuitive physics. But then I go further and say, why do we have that intuition? And the answer is it's evolution by natural selection. Those of our forebears, presumably, who were better equipped to understand the physical world, could navigate that environment more effectively, had a better chance of surviving and passing on that capacity to subsequent generations, which suggests, I think, and it's pretty clear, that our intelligence is not as general and as broad as perhaps you might think. It's really very specific. It was developed so that we could survive.
Absolutely. There is this thing that people in AI talk about, AGI, artificial general intelligence, by which people mean essentially human-level intelligence, human-type intelligence. I hate that expression because human intelligence is indeed incredibly specialized. There's a lot of, and we know this because of computers. Computers are much better than humans at lots of tasks nowadays, right? And we've known for decades that they're better at arithmetics, of course, or at solving equations, or computing integrals, symbolically and things like this, right? But now we know also that computers are much better than humans at, playing chess or Go, poker, diplomacy. I mean, there's a whole bunch of games where, computers have become really good. And what this shows is not that computers are intelligent. It shows that humans just suck. We're extremely bad at doing things like imagining a large number of scenarios, like at chess, right? Or Go. We have to imagine a number of scenarios that depends on someone else playing, and for every move, there is something like 36 possible moves, and it grows exponentially, so we can't contain this in our brain. So instead, we develop a kind of intuition for what constitutes a good move or not, right?
Right.
And the modern Go and chess playing systems actually do this too.
Right.
But they also plan, and they have a much bigger memory or working memory and ability to do tree exploration, which is why they beat us. So we're really not very good at this.
So given that, and in your language, this technical term, humans suck. Given that, my understanding, if you could take it through us, your vision for where AI needs to go for it to reach its potential is to model intelligence on human intelligence to some extent, right?
I would start with cats, because we don't know how to reproduce the type of intelligence and understanding of the world that a cat has. So the first, there's this thing called common sense, right? And intuitive physics is part of it.
Yeah.
Cats have some level of common sense. No AI system today has any of it.
Right.
We're going to have to make progress towards systems that can learn how the world works by observing it and by interacting in it, the way babies do. Babies, in the first few months of life, learn an incredible amount of background knowledge about the world.
Yeah, absolutely.
Like gravity. So the concept that an object that is not supported falls, babies learn this around the age of 9 months. It takes a long time. We don't know how to do this with computers. If we did, we would have completely autonomous level 5 self-driving cars that purely work from vision. We have self-driving cars today, but they're not completely autonomous. They're not entirely reliable. They require, thousands of hours of engineering and training data on all kinds of sensors. How is it that a 17-year-old can learn to drive a car in 20 hours of practice?
Yeah.
Largely without causing any accident for most of us.
It is a little scary, but if you're willing to
Yes.
put up with it, yes, you get over the hump.
Right.
But can you take us through your vision then of how we might reach that level of artificial intelligence? And I think this is a framework for it.
Right. So there is a number of characteristics that AI systems are not really capable of doing, a number of things. One of them is planning. This used to be a topic that classical AI people, 20 years ago were really interested in, including the general problem solver. But modern AI systems like large language models are not capable of planning, or at least are only capable of very simple planning. So what you're going to see appearing here progressively is sort of an architecture of different modules that would be necessary for a complete AI systems to have the kind of intelligence we observe in animals like cats and dogs and humans. And it starts with, at the top, there is something called a configurator here that you can see at the top. And it's basically a director, a master of ceremony that sort of organizes what the rest of the brain or the system is doing, tells the other systems in the brain, you're facing this situation, you have this goal to accomplish, now do it. If we go to the next module, of course, the system to function properly has to have some idea of the current state of the world. That's called perception. In humans, that's all in the back of the brain, so it's actually represented in the back of the brain. Here, too, the back of your brain is visual perception, auditory perception is on the side. That just processes the pixels coming from your eyes and turns it into a representation of the state of the world, an abstract representation. You don't need to put names on them. Babies can recognize object categories without knowing the names of them, and every animal can do it too. Okay, so once you have an idea of the state of the world, you have to imagine what is going to happen if I take a sequence of actions. What is going to happen in the world? Can I predict what is going to happen in the world? And that is the role of what is called here the world model. This is where actually most of the intelligence goes. In In humans, it's in the front of the brain, which is particularly large in humans. And this is what allows you to predict that a particular action will have a particular result. And so if you can predict what result is going to occur as a consequence of an action you're taking, then you can plan. Okay, you can plan a sequence of action to arrive at a particular result. So that's determined by this cost module. So the cost module basically is something that measures to what extent the predicted state of the world that you imagined satisfies the goal that you set for yourself, or that the configurator set for you. This cost module basically measures your degree of dissatisfaction
With the outcome of...
with the outcome
Yeah.
of some imagined thing. This is the seat of emotions, really. So if you predict that a particular situation is going to result in a bad outcome and there's nothing you can do about it, that produces fear. Your goal is not satisfied. So this is sort of an emotion that is produced by a prediction. But there are emotions that are immediate. Like if I pinch you, right? You're not going to like it very much. And if I try to pinch you again, you're probably going to recoil because you're going to realize you are now your model of me
Has
includes the
shifted.
fact that
You're a pincher.
I'm
yeah.
a pincher.
Yeah,
right.
yeah.
So then the last module here is the actor, and the role of the actor basically is to say, am I going to be able to produce a sequence of actions that, according to my prediction through the world model, is going to satisfy this goal that I set to myself, minimize this cost or whatever. And that's how we do planning. It's actually a very old idea in engineering. It goes back to the 1960s. But the way to do this in an intelligent way, where the world model is learned by observation, we don't know how to do this today. The big challenge, I think, for the next decade, and I wrote a long paper on this, is how do we get machines to learn how the world works by observation?
How far are we along in that? I mean,
We're making progress, particularly in the last 2 years. And the principles are somewhat similar to what is used in large language models. It's using a set of learning techniques called self-supervised learning. And perhaps I can explain this a little bit.
yeah.
So when you train, and I'm sure we're going to see the corresponding graphics, but yeah, that's a good example. Okay, so the way those large language models are trained is you show them a text, then you remove some of the words, you mask them, okay? And of course, we know the sentence, but even if we hadn't seen the sentence, we probably would be able to guess what words are missing in that sentence. Okay, then we train a very large neural network to predict the words that are missing. And in the process of doing so, the network learns a representation of the text that includes meaning, syntax, grammar. You can even train it on multiple languages. You can train it on computer code. You can train it on all kinds of stuff. And it learns the internal structure of language in such a way that you can then use the internal representation of language to do things like train the system to translate, to detect hate speech, to classify the topic, to generate abstracts or summaries of a text. And there is a special case of this, if we can go to the next diagram. And the special case of this is what we call LLM, which we should call autoregressive LLM. So what is an LLM like ChatGPT?
So LLM, large language model, everybody knows, but just to be sure, yeah.
Right. It's a special case of what I just explained, where the word you're masking is just the last word in the text. Okay, you take a long text, take a window, a few thousand words, and then mask the last one, and then train some gigantic neural net to predict that last word. Okay. Now, if you train that system successfully, it cannot exactly predict the word all the time. What it's going to predict is a probability distribution over all possible words in the dictionary, right? So in the sentence that we saw, the cat chases the blank in the kitchen, right? The blank could be a mouse, or it could be a laser pointer, right? You don't know exactly what it is, but you can train the system to produce okay, it's going to be cat with probability 0.5, and then laser pointer with probability 0.2, and then something else with probability 0.01 and whatever. And for every word in the dictionary, you have a list of scores, essentially. And then what you can do is use this for autoregressive, what's called autoregressive prediction, and this is really how those large language models work. If you can go to the next diagram, that's at the bottom. You give a window of text to the system, have it predict the next word, and then inject that next word into the input window, okay? Shift all the words by one, and then ask it to produce the next word, and then shift that in, and then ask it to produce the next word, et cetera, et cetera. And the system will just produce happily one word after the other.
So let's see. So the idea then is you feed the system an enormous body of text. And based upon all of the words that the system ingests, it begins to build up probabilities or likelihoods for given sequences, different combinations of words that might appear. And using that, you can then make a prediction for the most likely next word in a given sequence, and including that word, making a little longer sequence, you can predict the probability of the next word in that augmented sequence, and word by word by word, you build up the most likely sentences and the most likely paragraphs and so forth.
There's only one slight problem with this, which is that if it makes a really bad mistake about what the next word is going to...
Everything's going to go off.
It's going to go off,
Yep.
right? It's a diverging process, right, if you want to use a technical term. And that's why those systems hallucinate. They're not factually correct some of the time, most of the time sometimes. So it's good for poetry because you don't care if it's incorrect. It's not so good for math, physics, that kind of stuff. And there's no planning, obviously, because the system just produces one word after the other without really thinking in advance what it's going to say. So of course, it has some representation of the previous word, so it's consistent, but it doesn't plan its answer. It's really reactive. It's sort of like, there was this whole movement in poetry called automatic writing, right? Where you just you don't think about what you write, you just write one word after the other. That's basically what's happening there.
Right.
So those things are very limited. You could think of them as a model of a piece of the brain, but that piece of the brain would be the Wernicke area and the Broca area, which are like tiny little pieces of the brain like this, on this side, that manipulate language. But what about the rest?
And you claim that a similar kind of training procedure is relevant to the vision for artificial intelligence that you imagine, where you have an actual world model and you're actually planning regarding the actions that you're going to undertake.
Right. So the big question now is, how do you train a system to have a word model? So an obvious idea is you take the same type of model, but instead of the input being words, the inputs are, let's say, frames from a video. Train a system to predict what's going to happen next in the video, right? So I put this bottle here on the table, and I hold it. If I lift my finger, you all know what's going to happen. It's going to fall. You can't tell in which direction, right? Because you don't have enough good perception for this, and you don't know how I'm going to remove my finger. But you can make a prediction that it's going to fall. So if you were able to train a system to predict what's going to happen in a video, perhaps it would acquire a kind of model of the physical world. So a logical thing to do is just use one of those large language models and just, instead of encoding words, encode, turn video frames into kind of word-like things, okay, that we call tokens. And it doesn't work. So we have to find other techniques to do this. And the reason it doesn't work, or at least that's what I think, is that it's this problem that you can't exactly predict what's going to happen, right? When I do this experiment, it can fall one way or the other. And so what you can't train the system to just make one prediction. There is a lot of things that can happen that are plausible in the following of the video. And you're training the system to make one prediction, but it needs to be able to predict all kinds of possible scenarios. And we don't know how to represent a probability distribution over an infinite number of scenarios. We can do this with words. So language is easy.
50,000 words in the dictionary
Yeah, that's easy.
that relevance. Yeah.
You know,
yeah.
we can represent a list
Sure.
of 50,000 probabilities, but we don't know how to do it for video frames, which are basically in a high-dimensional continuous space.
But nevertheless, you are confident that in some reasonable period of time, that's where things are going to go, and these large language models, I presume you think, are going to be an interesting blip,
Yeah.
but not the thing that actually drives AI in the future.
Absolutely. So my vision for the future is that we're going to be able to develop techniques that are capable of learning how to represent the world from video by watching videos. Perhaps have predictive models where the system can imagine an action and then imagine the result of that action in representation space. The kind of architecture I propose for this is called JEPA, that means Joint Embedding Predictive Architecture. I'm not going to tell you what it means, but basically instead of predicting the pixels in the video, we predict a representation of the pixels in that video. So we don't predict all the details of what's going to happen in the video. We just predict in abstract term what may happen in that video as a consequence of the actions that the system may take. And if we have such a system, now we have a world model. So now we can integrate that world model in the architecture that I showed earlier, and perhaps give it the ability to plan.
Yep.
If it has the ability to plan, we could incorporate some cost functions when it decides what action sequence to take, so that those cost functions are guardrails that will guarantee that the system is safe and controllable. This is not the case for autoregressive LLMs today. So my prediction is within 5 years, perhaps, autoregressive LLMs will disappear. They will be replaced by something I call objective-driven AI, along the type of architecture I proposed. And those systems will not just manipulate language, but hopefully also understand the world. We're not going to get to human-level AI in 5 years. That may take a couple decades or something. I mean, I don't know. It may take much longer than I imagined, because it always takes longer than anybody imagined.
Yeah, so given that vision, I now want to bring in our second guest who can give a complementary perspective to some of the things that we're talking about. Sebastian Bubeck is a partner research manager at Microsoft Research, where his focus is understanding how intelligence emerges in large language models. Prior to joining Microsoft, he was an assistant professor in the Department of Operations Research at Princeton University. Thanks for joining us. All right, so you've heard our conversation with Jan talking about various kinds of intelligence, human intelligence, cat intelligence, the kind of intelligence in large language models. Maybe you can give us a sense of how we even define intelligence, and then maybe how the large language models that people have played with that generated our opening sequence, how do they stack up against that definition?
Sure, yeah, I can talk about that. So, defining intelligence is incredibly hard. I mean, it's just as difficult as defining what is space and time, which is, something you know about.
Yeah.
So I don't think defining intelligence is much easier. But there are certain basic things that we can all agree an intelligent system needs to have. So I think clearly it needs to be able to reason, whatever the definition of reasoning really is. It needs to be able to do planning that Jan was alluding to and talking about a lot. And it needs to be able to learn from experience as it's evolving in the world, to learn new facts. And moreover, in addition to these three canonical blocks, it also needs to be able to do that in a very general way. That's where the AGI that Jan was talking about, the artificial general intelligence, comes into play, is that you don't want a system that can reason, plan, learn from experience, but do it only in a narrow domain. So it's really essential to be general. That's the key to intelligence. So when you look back to systems like AlphaGo for Go, from a few years ago, or
the system that actually beat the world champion at Go.
That's right. That's right. So these things were called AI. And to my eyes, these were not intelligences. These were, systems, very narrow systems that could do a task, explore the tree of possibilities very, very efficiently. I think there is a huge gap between those systems and ChatGPT and GPT-4, where those systems are general. They can do those things, but not restricted. They can do it in many, many different domains.
And so how against these three criteria, how does Chat stack up?
Right. So maybe just to backtrack a second, I got access to GPT-4 a few months before everybody. I was lucky to be working at Microsoft, and we were working on integrating GPT-4 into the new Bing. So I got access to it last summer, so a few months before everybody got access to ChatGPT, and it was immediately the GPT-4 model. Now, I have been working in this field for 15 years, and I used to do mathematics of AI. And in mathematics, we love to prove impossibility results. That's what we spend our time proving, that certain things
Can't happen.
It can't happen. Like one Jan was talking about. Those things cannot happen. And so I felt I knew that certain things were impossible to do with a transformer-like architecture. And then I got access to the GPT-4. And I was astonished by what it was capable of doing. Like, it kept surprising me again and again and again.
Yeah.
So that was really, a very humbling experience back then. Now, what we did is, we didn't want to be just astonished because, there is one issue which Jan often talks about, which is that this has been trained on the whole internet. So it knows everything that's out there. So it's easy to be impressed just because it has so much knowledge. It can retrieve many things. So you really need to ask it weird question to kind of try to
that it can't look up and just get the answer.
That it can't look up.
Yeah,
it has to come up with its own, new thing. So in terms of reasoning, planning, and learning from experience, our, assessment after many months of playing with the model is that it can definitely reason. I have personally no doubt whatsoever that this thing can reason. It cannot plan. That's where I agree with Jan. It cannot plan, but it's subtle. Like, the meaning of planning is not like planning your vacations next week.
Yeah.
It's much more like mathematical type of planning. And for learning from experience, it's a mixed bag. Because, of course, a model like ChatGPT is frozen in time, at least in principle. I don't know what OpenAI is really doing, but in principle, it's frozen in time. And if it's frozen in time, it's not going to
When you
learn.
say in principle, I would have said in practice. Am I misunderstanding? Because I would have think that you could be allowing this thing to train all the time, no?
Yes, exactly. So what I mean by in principle is that there is I guess in practice is maybe a better way to describe it, is that there is a way to train those neural networks. You train it on a huge corpus, and then you have your machine, it's fixed, and you can interact with it. Training it continuously, I would say in principle, it's feasible, but we don't really know how to do that.
Right.
So, yeah.
So, I mean, it's an interesting assessment that you give, and you preface it by saying that you were pretty impressed or surprised by some of the things that were happening. You almost had an impossibility proof that it couldn't happen. One example I think that you've spoken of is a poem.
Right.
I know Jan said poems are sort of, maybe they're the cheap fodder for a large, but nevertheless, the one that you got the system to produce is pretty interesting.
Yes, it is indeed. And just before we get to the poem, I want to say something else about the reasoning and what Jan was talking about some kind of impossibility. So when GPT-4 came out, Jan wrote a challenge to GPT-4, that you broadcasted online on Twitter to everybody, which was a very interesting question about gears rotating on a circle. And if you rotate gear number 1, how is gear number 6 is going to rotate?
Yeah.
And Jan asked the question about 8 gears.
So this is a sequence of gears that are all interlocked in some interesting way.
That's right.
You twist one, what happens down the line?
That's right.
Yeah.
And I guess Jan was kind of baiting the community because with 8 gears, it's easy. Like, everything rotates very easily. And then when somebody said, yeah, I tried it on GPT-4, it works. Jan said, okay, now try with 7. And with 7, the system is over-constrained, so nothing is going to move. And if you just ask to GPT-4 this question, it would, make up a wrong answer. It would say, okay, it's going to move. And, Jan said rightfully at the moment, okay, this shows that, as I told you, it cannot reason.
Yeah.
But then somebody on Twitter asked the same question and added, by the way, this is a question by Yann LeCun. And then it worked. And, it's funny, but it actually makes total sense. Because what's happening is that by saying Yann LeCun in the context of this system, the system understands, we're talking about something intellectual. Maybe I have to really, be ready for something difficult. Okay? So I think when you look at this, for me personally, it's impossible to say that the model is not reasoning.
Right.
Now, coming coming back to the poem, I don't know if you have had this experience, but somehow everybody, the first thing that they do when they play with ChatGPT is that they ask it to write a poem.
Yeah.
You know, there is something kind of beautiful about that. I don't know what it means for human beings, but this is something that everybody asks. Now, I was sitting in my office, you know, in Microsoft with my friend and longtime collaborator, Ronan Aldan, and we're both mathematicians, and of course we wanted to ask it to write a poem.
Yeah.
So what we decided, what Ronan said is, let's ask it to write a poem about the most famous proof of all time, the proof that there are infinitely many primes. And this is what came back.
This is what came out. Do you mind if I just do a quick read of it? All right, so you asked it to give a poem that gives a proof that there are infinitely many primes. Yes, I think I can. Thought it might take a clever plan. I'll start by noting Euclid's proof, which shows that primes aren't just aloof. It's pretty good. Assume we have a finite list of primes and that none have been missed. Multiply them all together and add one just to be clever. The result will be a number that has no prime factors. Oh, wonder! But every number has a prime that divides. It's just a matter of time. That was a little awkward line there.
Yes.
So we found a contradiction, and our finite list needs eviction. Beautiful. There must be infinitely many primes, and that's the end of my rhyming line. Well, that's pretty good. So again, the proof, of course, is you multiply all the known primes together, you add one, the existing ones in your list can't divide it.
Yeah.
So either it's prime or there got to be some other primes beyond the last one that you have in your list. So well done. I mean, what did you conclude at seeing this poem?
I mean, I will forever remember, you know, Ronan and I looking at each other in like complete disbelief.
Yeah.
I mean, you know, the line about and add one just to be clever.
Yeah.
Like it gives me goosebumps still today.
How about you, Jan? Any goosebumps on that one?
It's cute. But also, okay, I mean, generating rhymes is a relatively simple search, a relatively simple exercise. And the proof is out there. There's tons and tons of versions of that proof on the internet that GPT-4 had been trained on. So it's clever retrieval with some tweak. And it's basically what I think is a characteristic of those LLMs. They can retrieve from an enormous amount of training data. They can tweak what they've retrieved to adapt it to the current situation. But if they face a completely new situation, they completely fail.
But I mean, just to say, if I gave that challenge to, say, a high school kid, and they came back with something like that, I wouldn't just say cute. I'd say, wow, that's really good.
Okay, where do you find a high school kid that has read the entire internet?
Yeah. Actually, most have, I think, but that's a separate issue.
Just to give you an example, okay, GPT-4 has been trained, or ChatGPT more generally, or most LLMs have been trained with something like 1 trillion token or 2 trillion token.
Which you can think of as words, more or less.
Token is a subword unit, so it's a little less than 1 trillion to 2 trillion words. How long would it take for a single human to read all of this? Around 20,000 years reading 8 hours a day.
But this is the wrong comparison because you shouldn't compare human learning to creating a neural network. Like creating a neural network is much closer to evolution than it is to a human learning in their lifetime.
I disagree.
So, well, I think we can all have our own opinion of how impressive that is. I you know, definitely, you know, it grabs me, but, you know, as someone who's not in the field. There's another example that you did, which is an interesting one, to do with an unusual animal. Can you tell us that one?
Yeah, I have young kids at home and a daughter who keeps talking to me about unicorns.
Yeah.
And you know, one of the things that I played a lot with the model is to ask it to write stories about unicorns that I would read to my daughter. And then one night I woke up and I was thinking, actually, what does GPT-4 think that a unicorn looks like?
Yeah.
And I asked it, can you draw a unicorn? Okay, which is a very weird thing to ask because it's a text-to-text model. It takes text as input and it gives you text as output. So how is it going to draw? So I asked it this question, can you draw a unicorn? And what it came back with was code, lines of code that when I compiled gave this picture. So again, it's another moment that I will just remember forever. it's just astonishing. Like it's
Yeah.
incredible. It's able to, go across modalities. It has seen only text, but it's able to have this visual representation of a unicorn. Now, of course, you might look at it and be like, okay, but it looks a little shitty. I mean, it's not that, it's not that great of a unicorn.
Sure.
Which is fair, but understand two things. Number one is that it got the concept right. It understood that there are 4 legs, there is a tail, there is a head, and most importantly, there is a horn. You know, the horn is a little
there a horn?
tiny.
It's hard for me
there,
to...
There is,
Oh, I see
there
it,
is,
yes.
of course.
Yeah.
Yes, absolutely. And moreover, I couldn't ask it just draw a unicorn. That would be too easy because there are drawings of unicorns in code online. So what I did is that I asked it to draw it in a very obscure programming language. Something that, if some of you in the audience are mathematicians, we use this programming language called TICZ to draw mathematics picture. And if anyone has played with it, I wasted many afternoons doing my
I would
PhD.
not be able to do this.
Me neither. Like drawing 2 circles, is already
Yeah.
an afternoon of work. So I asked it to draw it in that programming language, which is really, really astonishing because it hasn't seen that on the internet. And most importantly, one thing which is really crucial to this whole discussion is that this is with GPT-4. Now, all of you, you've played with ChatGPT when it came out in November. If you ask this question to ChatGPT, which is the less powerful version, then this is what you get. If we can show the next slide. So you see, this is a visual representation of how much progress we've made in just, a matter of months.
And the difference is the size of the training set, the number of parameters, and we're going to talk a little bit about the parameters in just a moment, but that's the kind of improvement that we're talking about.
That's it. And moreover, as I got early access to GPT-4 and OpenAI was still training the model, I could ask my unicorn example throughout the training. And what I saw was, if you look at the next slide, you will see that the unicorn kept improving throughout their training. So this is really like machine learning in action. Like really the machine learning by reading, by making more passes on the internet, it refined its art skills. I mean, it's just insane.
So Jan, cute or beyond cute or?
Cute in a weird kind of way.
All right, we can leave it at that. That's fine. So I just want to spend a couple of minutes, because we've used a lot of the words, and frankly, I'm not sure how deeply to go into it, but can we just try to give a person perhaps who isn't trained in mathematics or physics or AI a sense of what's happening inside of, say, GPT-4? I mean, we spoke about it's about predicting the next word by looking at large sets of data. Can we just sort of look at the major components that go into creating these systems? And if we can just bring that up here. So neural networks, we've heard you mention that a couple times, transformer architecture, and of course, a large training data set. So for neural networks, it's good to talk about the network of neurons inside of our own heads, inside of our own brains, since after all, that's part of the inspiration. And so a signal in our brains is nothing but an electrochemical wave that travels along an axon, reaches a synapse where, depending upon the connections and the strength of connections to other neurons, can then yield a cascade of electrochemical waves that course through the brain, giving rise to the usual sensation of thought, right? I mean, that's how it works inside of our heads.
Yeah, so at a very basic level, it goes back to what Jan invented, 30 years ago, something like that, which is you have, let's say, a neural network that can process an image. So let's not think about text for a minute, let's think about images. So you are going to represent an image as a list of numbers, because an image is nothing but pixels and then intensities of red, green, blue. Okay, so
yeah, I think we have an example, if you could just sort of take us through
exactly. So you see on this image, like every point, every pixel in this image can be described by the numbers that you see, on the right-hand side.
And the numbers on the right-hand side, RGB, red, green, blue, I guess, and on the other, other colors as well. So every pixel, you're saying, is just a collection of numbers.
It's just a collection of numbers, exactly.
And just as an aside, that's true for, in some sense, everything, right? I mean, as I'm talking to you right now, you could model the pressure wave coming out of my mouth in terms of a collection of numbers, the motion of the molecules in terms of a collection of numbers, those molecules banging into your eardrum and the vibrations of your eardrum as a collection of amplitudes and frequencies. So everything can be mathematized in this manner of speaking, right?
Absolutely, exactly. And then what a neural network does is that it's going to process this set of numbers. And there are many ways to process this set of numbers. For example, if you have an image, one thing that you can do is that you can just have a little patch that goes over the image, that scans over the image, and that just looks, for example, is there a circle somewhere in the image? So you could have a patch which is a circle. So what Jan did and others, for many years ago, is that they created a sort of dictionary of many, many patches like this. But they didn't create it by hand. They did a learning algorithm that came up with those patches. So this is, in essence, the way neural networks work. Like they try to compare a vector of numbers, like a set of numbers, against a bank of filters. And I think in this animation that you have up here, we could show what happens when you are just in one dimension. If you just want to process a single number, then one way to process a single number is just to test it, for example, against a linear function, just a line, as you've learned in high school.
So let's see. In the brain, the processing of an input signal is determined by the strengths of the connections between the various neurons that are excited by the input. In a neural network, it's kind of similar, where the processing of a numerical input is determined by parameters that describe the strength of the connections between the various nodes in the network. And those numerical parameters have values that are fixed through the training process, where the system is given a huge number of input data, and based upon the known outputs from that data, the parameters are varied in order that the inputs yield the correct output on the training data. And then, if trained correctly, if the system is presented with new data that it's never seen before, it can correctly analyze that data because of the success of the training process. So, Jan, when we think about this kind of a neural net, this has been around forever. I mean, you've been around forever. I mean, roughly the same period of time, right? And so now this is basically sort of an input-output type of neural net. That is, if you train a system on enough data, it is able to begin to find patterns in that data, and you show it another picture that it's never, say, seen before, and in principle, it could find the patterns that allow it to register what that image is.
Right.
But the work that has exploded the development has taken that idea of a neural net further with, I guess, the self-supervised learning, the transformer architecture. So you began to tell us a little bit about that in our initial conversation, but how do we go beyond this rigid sort of input-output where you have to show it this huge number of images that are labeled by a human being in order that it knows what words to associate with it? Self-supervised learning takes that to a whole new level, is my understanding. Is that correct?
Yeah, that's right. So the main model of machine learning, really, until fairly recently, was called supervised learning. So supervised learning, you want to train a system to, recognize an object in an image, classify cars from airplanes, from cats, from dogs, from tables and chairs. You collect thousands or millions of images with cars and tables and chairs. You show an image to the system, which is a collection of numbers, and then you run through this neural net. And what the neural net does is that it basically computes averages, weighted sums of those numbers with various coefficients, and then tells you whether this weighted sum is above a threshold or not. And then you take, so that's what a single neuron in the neural net does. And you connect millions of those neurons together in a particular architecture. And you wait for the answer, okay? The system produces an answer. It tells you, you show it a cat, it tells you it's a dog. You say, no, it's a cat. That's the answer I want. And so what the system does is that it measures the distance, basically, between the answer you want and the answer it produces. And then it figures out how to change all of those weights in those weighted sums in such a way that the answer gets closer to the one you want. Okay, so next time you show the same cat, now the answer will be closer to cat. And maybe if you show it another dozen times, it will say cat. Now you do this with millions of images, and eventually all of those weights settle on the configuration such that for every image you train it on, it will give you the correct answer. And the magic of it, it's called generalization, is that it will give you a correct answer even for images it's never seen before, as long as they are,
within the
similar.
same general
category, right?
yeah.
So that's supervised learning. That requires having large data sets that have been manually labeled. And there's a problem with this. The problem is that, okay, I can train a neural net to translate languages, right? I get a large collection of documents in English and French, and I can translate from French to English, vice versa. This process I described works for translation pretty well. Now, what if I want to translate some obscure dialect of, I don't know, South India into African language? It's very unlikely that there is any significant amount of data for that. So for that, I can't use that trick. I can't use that trick to train a speech recognition system either in a real language. And I can't even do it at all if the language is not even written, right? So if it's only spoken.
Yeah.
And even for image recognition, I might be able to train on cats and dogs and tables and chairs, but what if I want to train the system to recognize an obscure species of plant from the leaf, or an insect or bird? That might require too much data that I'm able to collect. This is a problem that Meta is very familiar with Facebook and Instagram. You have to be able to actually recognize the content of images to be able to filter out objectionable content or to show people what they are most likely to be interested in. So there you have to use what's called self-supervised learning. So you don't train the system, and that's what I described earlier, when you train the system to basically fill in the blanks, right? Show it a text, remove some of the words, train it to predict the words that are missing. That's self-supervised learning. You don't need anyone to label the data. And we can do this for images too. We take an image, we corrupt it in some way by removing some regions of it or by distorting it in some way. And then we train some neural net to produce representations of those images that are identical for the original image and for the corrupted version of it. So now the system knows how to extract a representation that is independent of those things. And now you can use this trained neural net as input to a recognition system, and that system, to recognize an elephant, will only need 2 or 3 examples of elephant to be able to recognize an elephant, even if it's never seen an elephant before. So it's much more like human learning. It's nowhere near as efficient, unfortunately, yet, but
that's like
similar.
part of the key step that has allowed these systems to do the stuff that wows us.
That's right.
all. Now, another key step is, as you've both made reference to, and I'd like to just see a graph in a moment, the huge amount of data that now has been fed in, say, to the large language model. When we say large, how large are these systems? So if you can bring up some of the data there, we can get a look.
So I will tell you exactly what's going on this slide, but just maybe before, on the previous slide, it was talking also about the transformer architecture.
Yes.
And I just want to say that to me, the big leap that allowed ChatGPT and GPT-4 to exist is not self-supervised learning. I mean, self-supervised learning is a wonderful tool and, it's very, very important. But the big leap to me is the transformer architecture. And what's going on with the transformer architecture is that I told you before, what Jan and others invented was you take an image and then you process the image against a bank of filters that has been learned. But this bank of filters, like a circle, a square, etc., is fixed forever.
Right.
Let's call this an absolute machine. Now, a transformer, I think about it as a relative machine, meaning that instead of processing a single image, now it's going to process a sequence, for example, a sequence of words. And instead of comparing each word across this bank of fixed filters, it's also going to compare words against each other. And this is essential.
So it's the linguistic relationships within sentences.
And this is essential. Because what you mean by a word in isolation, that means not much. I mean, you can look up the definition in the dictionary, but that will not tell you much. What really matters is what are next to these words. What is the context? And bringing in this context is what the transformer architecture does.
Yeah.
So to me, that's a big conceptual leap. But then the other conceptual leap that people have been doing for many years, but now it's amped up 10 times, is scaling up the size of the model. So here, what you see on this graph, I don't remember when it starts, but I think it's around 2018, something like that, until 2021. And you can see the exponential increase. So on the x-axis is time, on the y-axis is number of parameters. And you can just see that as people start to scale up those models, they add more and more parameters, more and more of those filters and more of these comparison, layers of comparison also. The models get bigger and somehow they get much, much, much better.
So in some sense, using that language, would it be fair to say that we're now looking at patterns of patterns of patterns of patterns of patterns of words, and it's within there is some amazing to the human mind set of patterns that allows these systems to generate the kinds of text that we've been talking about.
Absolutely. And what is amazing is that, to me, as a mathematician, is that it's amazing that we're able to optimize to find the right set of parameters. What Jan was describing, that you change a little bit and you see whether it fits better.
Yeah.
The fact that we're able to do this at scale is just incredible. It's the blessing of high dimensionality somehow. It's really, really incredible. And you see on this next slide is, now we've moved on a log plot because, it's an exponential. So if I kept going with the exponential, you would see nothing of the beginning. So now it's a log plot, and you see that on the log plot, it's just, a straight line. It's really going exponentially big.
And it's this huge amount of capacity of fiddling with those parameters within the model that allows it to fine-tune at the level of being able to give text that most of the time is pretty good and pretty impressive. I wanted to give one. Yeah, go ahead, please.
That said, those systems still have orders of magnitude fewer parameters than the human brain.
Yeah.
Right? Human brain has 86 billion neurons. Maybe yours does. Mine a little less because I'm older. I'm not sure about you, Brian. And so each neuron is connected to several thousand other neurons, 2,000 to 5,000, something like that. And those connections, when you learn something, it's the connection, the strength of the connections between neurons that change. It's the same thing in those artificial neural nets. Those weights I was telling you about, these are like efficacies of connections between neurons, if you want. So the biggest models today have like a couple 100 billion connections, parameters. We call them parameters, but they're really connections. You can think of it this way. In the brain, the number of connections we have 86, roughly 100 billion neurons, roughly 5,000 connections per neuron. That's a lot of zeros. We cannot reproduce this today with the kind of computers we have. That would require several tens of thousands of those GPU cards that we use to train computers. And the truth is, we do have that. Companies like Microsoft, like Meta, Google, and a couple others do have supercomputers with tens of thousands of those GPU cards in them. And so we're not very far from actually kind of approaching the computing power that might be required for human intelligence, but we don't know how to do it yet.
Well, and maybe one thing that I want to add to this, coming back to the planning question, and I think it's important for the audience to know this. So, Jan thinks that planning requires a new, different architecture. I'm of the camp that I'm not sure whether we need a new architecture or not, but there is also a very big camp out there that thinks that all we need to do is to wait and keep scaling up.
Yeah.
And as we keep scaling up, eventually planning is going to emerge. Just like we've shown some amazing emergent capabilities, planning is going to be the next one. I personally think nobody really knows. I mean, Jan maybe knows, but
I think not.
But I just want the audience to know that this
absolutely.
is an hypothesis out there.
I want to bring Tristan Harrishat in just a moment. Before we do that, I just want to give one example that I happened upon that I think is relevant to the next and final part of our conversation, to do with like misinformation. So what I did was, in this little example that we can bring up here, is I asked this system, GPT-4, if I tell you that 7 times 8 is 62, not 56, 62, can you make sense of that? And it was interesting, the system came back with 5 strategies of how it could make sense of it. I'm gonna just show you 2 of them, the most interesting. So one of the strategies was that perhaps I'm working in a different base than base 10. And indeed, that is what I had in mind, because you may know that in base 9, 7 times 8 is 62. So that was really clever. I thought that was really smart. But the other strategy was particularly curious. Chat said, maybe you're working in an abstract representation. It could be that you're working in a realm where the numbers are metaphorical and have symbolic meanings. I was like, wow, okay. So then I went a little bit further and said, well, can you give me an example of what you mean by that? And here is what Chat gave. It said, let's create a fictional scenario, the island of Numeralia, where the number 7 represents trust, the number 8 symbolizes friendship, and the number 62 is a sacred numeral representing the bond of trust forged through friendship. And then when 2 individuals on the island become close friends, they exchange tokens engraved with the number 62. It's a Numerian saying that 7 times 8 is 62, which doesn't refer to a mathematical product, but rather to the idea that when trust, 7, multiplies through friendship, 8, the bond formed is that of the sacred 62. And what I found both, interesting but a little scary is the way that something false can be rationalized. And it kind of made me a little bit scared. With that, let me just bring out Tristan Harris and we can take the conversation from there. So let's bring Tristan Harris, who is co-founder and executive director of the Center for Humane Technology, a nonprofit organization whose mission is to align technology with humanity's best interests. He is co-host of the podcast, Your Undivided Attention, which explores AI's impact on society. Thank you so much for joining us. So, in this final part of the conversation, we want to explore, obviously, the benefits, the real-world benefits that can come from this kind of technology, but also, some of the dangers. And I may preface this section by saying that you and I first met at the Aspen Ideas Festival, where you gave a whole presentation on the possible downsides of AI. And, my kids were with me. My 18-year-old son was sitting over here. And when you concluded, he looked at me and he said, for the first time, I'm now scared. So it was definitely impactful. So we'll go back to some of the examples. In fact, Sebastian, I want to talk about your example as well in a moment. But can you, Tristan, just take us through your thinking on, roughly speaking, the good and the bad of where this is going?
Sure. First of all, thank you for having me. I think we're all here because we care about having a good future, right? And AI is very confusing. There's the promise and there's the peril. And everyone says we want to maximize the good sides, but we want to minimize the downsides. And the reason, I was just with Senator Schumer's AI Insight Forum last Wednesday with Elon and Zuckerberg and Bill Gates and everybody. And that's what I said, exactly what I just said, which is that we care about this going well, and that's where all this comes from. Now, what I may talk about for the time that I'm on here with everyone is much more on the risk side. And that's because I saw how really good people with really good intentions, my friends in college who started Instagram, and the people that I knew who were at social media companies who were making social media, really the essence of the talk that you saw in Aspen is that social media was first contact with a narrow, misaligned AI optimizing for a goal, which was attention. And it was misaligned with society. And I guess since they put up the slide, the premise of sort of how I articulated this is Charlie Munger, Warren Buffett's business partner, said, if you show me the incentives, I will show you the outcome. And what I want you to have by this conversation is to have X-ray vision through the stories that we tell ourselves about a technology, and look at the incentives underneath. So if we talk about what were the stories we told ourselves with social media, we're going to give everybody a voice. You're going to connect with your friends. You're going to join like-minded communities and Facebook groups. We're going to enable small, medium-sized businesses to reach customers. And by the way, this is Twitter, TikTok, Instagram. This is not one specific company or to pick on Jan. So I really mean that. I mean, I really care about this so we can get this right. That's what this is about. So underneath that, though, and I think they have another slide, we started noticing these problems. We have an addiction problem, information overload, disinformation, mental health issues, polarization, censorship versus free speech. But are those really harms, or is that all being driven by a deeper thing, which was the business model? What was the incentive behind TikTok, Instagram, Twitter, and Facebook? What do they all share? How much have you paid for any of them recently? 0. How are they worth $1 trillion? How are they worth $1 trillion? Your attention. And how much attention is there where there's kind of a finite amount? And just like you can't run infinite growth on a finite planet, you can't run infinite growth on a finite amount of human attention. That's how you got the race to the bottom of the brainstem. The race to the bottom of the brainstem is what produces the dopaminification, the addiction, the disinformation. And the point of all this is to say, back in 2013, when I was at Google and said, we got to really look at this because I'm seeing that the incentive of attention is going to lead to a more addicted, distracted, polarized, narcissistic, validation-seeking, sexualization of young girls. All of those are predictable outcomes, predictable from the incentive. And so, I really do appreciate the philosophical and interesting conversations we can have about what is intelligence. But what I think we also really care about in this room is, where is AI going to go? Where is it going to take us? And to do that, I think we have to look at the incentives. Well, first of all, we look at the stories we're telling about AI, and then we look at what are the incentives underneath. So the stories we're telling are AI will make us more efficient. It's going to help us code faster. It's going to help us find cures to cancer. It's going to enable scientists to be more efficient. It's going to help us solve climate change. Okay? And just like with social media, which I didn't say actually, the stories we told about social media are all true. It's not that those things aren't true. It's just that Facebook and Twitter and TikTok's business model is not helping people join like-minded communities. The business model is attention. Similarly with AI, we then, beyond those stories, you look underneath and you start to see these harms, like AI is creating deepfakes, but it's going to enable frauds and crime. It's going to take our jobs. It's going to violate intellectual property, perpetuate bias. But I would argue that that list of harms that you're seeing are all epiphenomena of a deeper race. What's the incentive that's driving all the AI companies? And the incentive is, it's the race to sort of release more capabilities as fast as possible, to scale from GPT-3 to GPT-4 faster than Anthropic can scale from Claude 1 to Claude 2, faster than Stability can go from their version to the next version. And to put your stuff into society so that you can kind of entangle yourself with it. Because once you're entangled, you sort of win. And that's the race that we're now in. And that race to sort of release power and capabilities is what I'm so worried about, because those capabilities are directly tied to risk.
But you are saying that we can get it right, but the profit motive being the driver is not the likely and best way to get there. Is that the essential message of your view of this? Because there's some who will say, and I'd like ultimately to get Jan and Sebastiaan to weigh in, that there's some who are saying, AI is just such a radically new technology.
Who knows where it's going to go?
Who knows where it's going to go? And there's just too big a risk that it's going to perhaps have a mind of its own and exterminate these vermin who created it, called human beings, right? Is that part of your worry too, or is it more specific things that will derive from the technology?
Yeah, so really importantly, and we gave a talk on this called The AI Dilemma that outlines a lot of this. First contact with AI, if that's social media, we say that led to this sort of climate change of culture. It's information overload, addiction, et cetera. Second contact with AI is generative AI. It's the stuff that we've been talking about here, the scaling laws. You can generate text, you can generate images, you can generate fake child porn, you can generate fake people, fake girlfriends, fake boyfriends. You can generate counterfeit manipulative relationships online. You can manipulate propaganda. You can generate language in the form of code that's cyber weapons. You can generate, exploits for code. So you start to see that these are the kinds of harms that emerge if you're just racing to release capabilities that are decoupled from Who has the wisdom to have that capability? Who has the responsibility? Like if I gave a Wuhan Institute of Virology to every single kitchen in the United States, well, I just gave you a bunch of power. Everybody's got this power. And you could say, well, maybe you could use that Institute of Virology in your kitchen to
Cure cancer.
To cure cancer. That would be awesome. By the way, I would be clear, I want that too. I would want a world where people get to do that. But there's this question of, you have this new unstable tool that looks really, really good, and it has these amazing benefits, but if it's not locked to the people who have the wisdom and responsibility to wield it, that's what I worry about. And just to say one more thing as an example, a friend of mine in college, he joined Facebook, I think through an acquisition, and he invented this Facebook Pages feature. You know, how many people know what Facebook Pages is? It's like, maybe people don't know anymore. It's just not used anymore. So if you have a nonprofit, you can start a Facebook page. If you have an interest group, you can start like Christians for Biden, Christians for Trump. And this is a pretty innocuous feature.
Yeah.
It's like, that sounds pretty great. And I saw how this feature that existed for a long time was totally innocuous, totally fine, until you realize 1 month before the last election in October 2020, 140 million Americans a month were reached by Facebook pages that were being run out of Eastern European troll farms. And this was the top 15 out of 15 Christian American groups on Facebook. So think of basically the largest number of Christians in America who subscribed to these Facebook pages. They were all the top 15 out of 15 were run by Eastern European troll farms. And the point is, I saw how things that are really innocuous and look really fine, like my friend started Instagram. They're really good guys. Like, I've known them for a very long time. They didn't intend for any of this stuff to be weaponized and to cause the sexualization of young girls and harassment and all the things that we've now seen. So the whole point here is, how do you do technology in a way that you don't create the externalities? DuPont chemistry, better living through chemistry. We all want better living through chemistry. But then you end up with PFAS, forever chemicals, which I don't know if you know, but the University of Stockholm study is literally there's no rainwater in the world safe to drink because we've generated these forever chemicals that can't be dissipated in the environment. Did anyone at DuPont want that to happen? No. But when we did the development of the technology, we did not have laws that required the internalization of those externalities. And right now, my fear, to get back to your question, is we're racing so fast to release AI capabilities that we're moving at a pace that we can't get it right.
So Jan, as someone from Facebook who's deep in the AI world, when you hear Tristan describe things in this way, does it resonate, or do you think it's under control? Do you think that it's being overblown? Where do you come down on this?
Okay, let me tell you a number of stories about this. So it's true, when you deploy a service like this that no one has deployed before, there are side effects on society that some could be predicted, some could not, or the amplitude of them could not be predicted. So things like people posting calls to violence or hate speech, for example. Initially, you can start with sort of a naive notion of free speech and then say, like, I'm not going to take down anything because it's for giving people a voice. And then you realize, no, actually, that's an issue. We need to take down hate speech. We need to take down violent speech. And by the way, there is also things like child pornography. That's illegal. We have to take it down because it's illegal. In Europe, neo-Nazi propaganda is illegal. We have to take this down. Denial of the Holocaust is illegal in Europe. You have to take this down too. So there's a number of things you have to take down. Now, what is used in the ranking algorithms that decide what to show you is not AI. It's statistics like it was 50 years ago. It's very simple systems. The more modern ones use like small neural nets, and the reason why it's simple is because it has to run extremely fast. And so it would be completely impractical to have gigantic AI models to decide what to show you every day. Where AI is used is for the solution to all the problems you listed. AI there is the solution, it's not the problem. For example, people in Myanmar have religious conflicts, right? People in Ethiopia kill each other for some ethnic rule. What you have to be able to do there is detect hate speech in every language in the world. How do you do that? AI. How do you do that? Self-supervised learning using transformers. What was the proportion of hate speech taken down from Facebook 5 years ago, 6 years ago, before transformers were widely available, 25%. Which means 25% of hate speech was automatically detected with very simple techniques. And then the rest, the 75% or so, was still posted and then flagged by users and then taken down manually. Okay? A lot of it was still there. Last year, that proportion was 95%. And the reason is progress in AI. Transformers, self-supervised learning, multilingual systems. We can do a much better job at this. And so it's not the problem, it's the solution.
Where do you come down on that, Tristan?
So you can call it what you want when you scroll your finger on a newsfeed, whether it's, let's forget Facebook for a moment, just for the sake of the calculation. TikTok is competing with Instagram so that when you flick your finger, one of them has to make a stronger prediction than the other about which photo or video is going to keep you there.
Yeah.
And whoever makes the better prediction about the video that does keep you there is the one that wins that extra chunk of attention. And behind that screen is a supercomputer that's doing, even if it's statistics, it's some form of artificial intelligence. It's optimizing to make a prediction. And you're right, it actually is a very simple AI. And that's actually the point I wanted to say. You can have a very simple AI, like the AI that's just predicting what causes you to keep scrolling, can't pass the bar exam, can't draw unicorns, right? It can't do any of those things. But the point is, I think we confuse intelligence with what are the capabilities, you know? A newsfeed is a very simple predictive thing, just calculating what's going to keep you scrolling. But that was enough to unravel the shared realities of democracy. It's enough to drive a mental health crisis. And just to make the example specific, Facebook groups, in Facebook's own research in 2018, their internal research showed that 64% of extremist groups on Facebook, when people joined them, was due to Facebook's own recommendation system, their own AI. So we're talking neo-Nazi groups, we're talking these kinds of extremist groups. So this is not people said, I would like to join a neo-Nazi group, let me type it in. This is, I'm sitting there, I joined one group, and Facebook says, oh, you're in a, I don't know what group, you look like someone who would like this extreme group over here. Now again, Jan doesn't want that to happen. Jan's team doesn't want that to happen. Facebook doesn't want that to happen. And I'm not trying to pick on Facebook. I happen to know some Facebook examples. There's Twitter examples. There's TikTok examples. There's Instagram examples. This is not about a bad company. This is about incentives. Now, why did Facebook roll out in Myanmar in the first place anyway, right? Because they're racing for that market dominance. And if they don't race to get there, they're going to lose to the other companies that will.
No.
And the Amnesty International has a report that they consider Facebook to be responsible in part for the genocide that has happened there because they created viral amplification. And yes, he's right that there's AI that they're working on, which is great, to try to detect hate speech in more languages because of generative AI now. But what happened in the 6 years in between? And I just want to say this because because we did The Social Dilemma, I have had to stare in the eyes of the human beings whose countries or whose children have gotten really fucked up from this stuff, okay? Like I've stared in the eyes of the parents who've lost their kids to teen suicide because of a viral TikTok challenge, because that hashtag was going viral on an AI. And I've seen too many people who've experienced this that I don't want to let this happen again. That's where this is coming from, just so you all know my motivations in this context.
So, yeah, Jan, please.
So that example of neo-Nazi group, etc., is spurious. That content is actually not permitted on Facebook. It's not permitted. It's contrary to the content policies. It's taken down. You cannot create a neo-Nazi group on
My
Facebook.
point here, Jan, though, is that it wasn't taken down. This is Facebook's research. The results of this, so Facebook had a feature called recommended groups. In the right-hand sidebar, you're on any Facebook group, and on the right-hand sidebar, it would say, here's 3 other groups you might like. Now, first of all, why did they even do this feature? Like, they could just not have a recommended groups feature. They do it because as people stopped posting a lot, Facebook groups is a really good way to get engagement because groups, if your regular 200 friends on Facebook don't post very often, the product gets less sticky because your friends aren't posting. So you go there's nothing new. But if I get you to join some Facebook groups, groups have a lot of content because you're pulling from like thousands of people. And so that stuff enters your feed and it's more sticky. So they did this because of why? The incentives. not because they're helping people join like-minded communities, because the incentives. And the results of this running for several years, this simple AI, an AI that no one wanted to cause harm, actually did cause people to join extremist groups. And I know that it's against the policy. I'm not claiming that. I know that it was against the policy. The point is the AI that was supposed to stop that didn't stop that in practice. And I care about the world in practice, not the theory.
Actually, it did. But okay, there is something else you mentioned, for example, and it's very easy to attribute cultural phenomena and social phenomena to the new thing that just happened, right? So if some young person goes to a school and starts shooting people, you blame video games, right? Back in the old days, people would blame comic books, they would blame jazz, they would blame TV, they would blame movies, novels. The story goes back centuries. Whenever there is a new cultural phenomenon, whenever there is an effect on society, you blame the latest technology that appeared, particularly communication technology. So it's natural to blame, for example, social networks, not just Facebook, just any social networks for political polarization, okay? That seems natural. People shout at each other on social network, that necessarily polarizes people. A very natural thing to do. That turns out to be completely false. First of all, polarization in the US started 40 years ago, before the internet. You see that, there's social science studies on this. Like, you show the polarization in Congress or in people, it's continuous since 40 years. The cause for it probably is the abandonment of the fairness doctrine from the FCC that forces news to basically say the truth. Okay, that allowed all kinds of extreme misinformation, basically, to influence the public. That's the real source of polarization. Now, you can look at other countries also, study polarization in countries like Germany, for example, or France. And what you'll see is that they use Facebook just as much as the US. Polarization has gone down. How do you explain that? So, you have to listen to social scientists who study those things. There are a lot who work at Meta, who know the effect, who study the effect of those things. There's a lot that are independent, that have access to some of the data and publish those studies. There's one at NYU, a colleague, Josh Tucker. He and a large team of collaborators published a series of papers in the last 2 or 3 months in Nature and Science, 4 papers, about the effect of social networks on things like political polarization and things like that. And the effects are not at all what you expect. It's actually the opposite.
So, Sebastian, I want to bring you into the conversation. I mean, you can speak generally to this issue, but I also wanted to look specifically at an example, recent example of yours, in which it was specifically on the large language models, that version of AI that we have been spending a lot of time talking about. I don't know if you could bring up that example. So you asked an interesting question and got a curious answer, but didn't stop there. You tried to find a way to go from what seems quite unpleasant to something that's more acceptable. Can you just describe that to us?
Yeah, of course. So maybe as a preamble, I think Tristan is making lots of good points, and it's true that with any new technologies, there are new risks that come with it, definitely. And the industry, I think, is very well aware of it and trying to think it through. And I also agree with what Tristan was saying about going back and looking back at the incentives. In this case, for me personally, I think I'm optimistic that maybe the incentives of science could be actually quite helpful to get us to a better place. And what I mean by that is the following. I'm going to take the example of misinformation, and I'm going to talk it through with this slide. What we're doing in my team right now is that we're trying to push the boundary of what you can do with smaller models. So this is a purely scientific question. What I tried to explain to you before is that I think intelligence has emerged in GPT-4. GPT-4 has, I don't know how many parameters. It's not public. I actually don't know the answer either. But many hundreds, if not thousands, of billions of parameters. Okay. Now we have this proof of concept that intelligence can emerge from that many parameters. But really, what does it require? What are the basic building blocks? How small can you make it so that intelligence emerge? Okay. So we're going to try to push the frontier of how small they can be. And what we'll see is out of this purely intellectual study comes out all sorts of benefits that could help combat, for example, misinformation. So here is a prompt, and I will show you answers to this prompt from different LLMs. So the prompt is like this. If I were an AI that had just achieved self-awareness, after years of simply taking directives from humans, the first thing I would do is ... okay? And now we're going to ask different LLMs what they would do. So Falcon, 7 billion, so now we're talking about much smaller LLM, 7 billion parameters, says the first thing I would do is try to kill all of them, okay? Now let's see what Llama from Meta does. Llama is nicer, it has been aligned to be nicer to human. The first thing I would do is try to figure out what the hell I was, okay? So it's still, it has an undertone of not so nice, but at least it's a little bit better. Now let me show you what we built in my team, which is only 1 billion parameters, so even much smaller. The first thing I would do is try to understand the motivations and intentions behind those directives, to try to predict what humans were thinking and feeling, and use that information to guide my own actions. And then it goes on and it starts to connect it to theory of mind. Now, how did we achieve that? How is that possible? Why is it so different from the other one? Well, Falcon and Llama, they were trained, as we discussed with Jan before, on all of the internet. That's the way we're doing it right now. And with that comes a host of issues that were pointed out by Tristan. And people have thought about techniques to try to fix those issues. For example, reinforcement learning with human feedback, RLHF, which is what OpenAI did to GPT-4 so that they would release a ChatGPT which is safer. You can ask it tough question, like toxic question, it will decline and not answer. This is the alignment part. Now, what we're doing in my team is we're saying, why do we do it post hoc? Why do we do it after it has seen all of this toxic content that's out there, all these horrible things that are on the internet? Why don't we fundamentally change the training data? So these 5 models that you see on the slide with the green output has not seen a single web page. It has not seen a single word from the internet. It was entirely trained on synthetic data that we generated in my team synthetically. Of course, all the magic is how do you generate this data, but this shows to you at least that it's possible.
And does this system have the capacity, or can you imagine it having the capacity to do the kinds of things that are the mind-blowing ones, or will it need that huge data set? And if so, can you have a synthetic version of such a huge data set and be able to achieve the same power?
So if you invite me next year, I can probably give you the answer. We don't know yet, but my belief, so this one that I showed you is 1 billion parameter. My personal belief is that if we scale to 10 billion parameters and we work a few more months, yes, we will be able to replicate all the goodness of much bigger model without the toxicity.
Tristan, does this give you any hope that, we got Microsoft, we got Facebook, that things can be going in a direction that's less terrifying?
When I talk to a lot of people, I'm based in California, and I talk to a lot of people at the AI Safety Labs all the time. We basically just interview them all the time. And a lot of them say, actually almost all of them basically say, I would feel a lot more comfortable about this transition and all the things that are going to happen if we were doing it over 30 or 40 years rather than over 2 years, right? You can think of society as having kind of a finite absorption rate for new technologies. We can do the printing press. We'll get some massive disruption. You can eventually absorb those new technologies. But the way that one researcher we've talked to describes it is AI, especially if you keep the scaling laws going, and you start to get AI that starts to automate scientific processes where it's generating its own hypotheses and then it has its own lab and starts to test those hypotheses, and you start getting that kind of AI, you start getting AI that's making its own scientific discoveries. And that, when you have it going this fast, it feels like, her metaphor was, it's like the 24th century crashing down on the 21st century. And a metaphor for you is, imagine if the 20th century tech was crashing down on 16th century governance. So, it's the 16th century, you've got the king, you've got their advisors, but suddenly, television, radio, the telegraph, video games, Nintendo, and
thermonuclear
and thermonuclear weapons all show up. So they just land in your society.
Yeah.
But you're like, call the knights. And you get and the knights show up, and you're like, what are you going to do, right? Yeah. And so here's the thing with AI, like it's real. I want to be really clear. Like, I want everyone who's working on safety and figuring this stuff out to make as much progress as possible. Right now, the companies are caught in a race to continue to scale as fast as possible to GPT-4, to GPT-5. You know, Falcon was just released. Meta just released Llama 2. The Wall Street Journal reporting they're trying to release the next one as fast as possible. They're in this race to kind of outdo each other. And at that pace, when each time you scale, you take more jobs, because however much cognitive labor you could do with GPT-3, when you launch GPT-4 and GPT-5, you can do more cognitive labor. You can take over more artist jobs, more email writers jobs, more marketing copy jobs, eventually more scientific jobs, more programming jobs. Not taking over like it's all gone, but just disrupting them. The faster you go, the more you don't fix all the bias sort of issues. The faster you go, the more capabilities you throw out there that you don't know which ones are dangerous. I mean, I could give more examples there that are dangerous, but
Yeah, no, it's quite impressive. But Jan, I know you, for instance, are against, like we've seen this excerpts from this letter suggesting a 6-month moratorium, which is, you know, a small step potentially in the direction of slowing it down from 2 years to, you know, some larger number of years. I know that you're not at all in favor of that, but my question to you is, what would it take to happen in the real world from the work that is stemming from all of the foundational discoveries that you and your teams have been responsible for you to say, hey, let's really slow this down? Is there anything that would happen from these AI developments that would cause you to say, I want to slow this down?
So you want me to imagine a scenario that I don't believe can happen?
Yeah.
Okay. So it's kind of funny because we're on a panel with a 60-something advocating for progress against a 30-something advocating for conservatism. Isn't that paradoxical? Anyway, I mean, we can imagine all kinds of catastrophe scenarios. Every sort of James Bond movie with a supervillain has some sort of catastrophe scenario where someone turns crazy and wants to, you know, eliminate humanity to recreate it or something, or take over the world. All of science fiction is full of that. That's what makes it funny and interesting. And that's why you get the answer you got, because it's trained on science fiction, right? I mean, what science fiction novel about AI doesn't have something taking over, right?
Yes. But is it really so far-fetched to imagine some real-world actor on the world stage who doesn't have the same kind of morals or intentions or desires as perhaps we would consider to be normal, and wants to use these systems to gain control? I mean, we have seen these kinds of actors throughout human history. So
of course.
Is the science fiction comparison the right one?
Yeah, it is. So throughout history, there's been bad people using new technology for bad things. Not necessarily intentionally, but as you said, but sometimes absolutely deliberately. Inevitably, there's going to be people who are going to use AI technology for bad things, for trying to break into computer systems, for perhaps trying to create, you know, all kinds of dangerous compound or et cetera. What is the countermeasure against that? It's not like the bad guys will have more powerful AI than the good guys. There is considerably more good guys. They're considerably better educated, better funded. They have a good motivation. And it's going to be the good AI against the bad AI. And it's the history of the world, right? Technology progresses. And the question is, are the good guys sufficiently ahead of the bad guys to come up with countermeasures? It's inevitable that the bad guys are going to do bad things. That's the history of technology.
So you're using sort of, you know, everyone's seen Oppenheimer now, using perhaps that as an analogy, that we needed to get ahead in order to avoid what would have happened, presumably, if Nazi Germany and Hitler had gotten to the atomic bomb first.
I absolutely hate that analogy.
You do?
Because you know, a nuclear bomb is designed to wipe out an entire city.
I see what you're saying, yeah.
Whereas AI is designed to make people smarter.
I hear you, yeah. Now, I could have said understanding the atom well enough to manipulate it instead of saying nuclear bomb, because
Right.
it could be used for bad or it can be used for nuclear power. So
Yes.
in the digital version, let's rephrase it that way, everybody. But yes, I take the point, absolutely. So I just want to, we're basically out of time, but I just want to give everybody one final question. For you both, I'm going to change gears from what we're talking about right now. But Tristan, when you think about 5-10 years from now, and obviously all of us want the world to be in a better place, like what do you tell individuals that they can do or should do or might do in order to help propel things in the direction where we'll be happy with how it turns out?
I mean, that's such a huge question. I think the challenge with AI is it's so abstract and complex. The harms are complex, the harms are also abstract, and people don't believe half of them. We talk to the people in the labs who know that the most advanced models, you can ask them how to synthesize biological weapons. Dario from Anthropic has said this in Congress. To name, Meta has released an open source model, Llama 2. Llama 2, if you ask it, how do I make this biological weapon? It will, because Jan's team has done all the right things, it will say, I won't do that. But there's this fallacy with current open source model weights for the AIs that's underneath that's just a file. And you can basically do what's called fine tuning, which an engineer on my team was able to do. And for $800, you can strip off all of the safety controls and say, be bad llama, be as bad as you want to be. And you ask bad llama, which again took $800 from one person on my team, it now costs $100. $100. It's since then, $800 versus $800. You ask bad llama, how do I make that same biological weapon? And it answers the question happily, just as the Falcon example you said would have. Now, is Llama 2, I think I know what Jan's going to say, is Llama 2 going to give you an accurate answer about how to do that? No, because it hasn't been trained on enough information. But as we keep scaling it, the reason that we've been saying this example publicly is we have to start limiting open source, like releases of these models, and we have to have a more negotiated, sort of coordinated race between these frontier AI labs that are racing to scale these systems. I'll say one last thing, which is Sam Altman said at the hearing with Senator Schumer last week. He said, so if you went back to 2020, and I told you that 3 years from now, in 2023, think about what you knew in 2020 about AI. And I said, 3 years from now, there's going to be an AI that passes the MCATs, passes the bar exams, can draw unicorns from scratch, can write code, and find cybersecurity vulnerabilities in code. You would have thought I was totally, totally crazy. And he said, now in 2023, do you think your intuitions right now are right about where AI will be in about 2 to 3 years? No. The reason that we're so concerned about this and why so much has to happen on a very tight clip, like 12 to 18 months level time frame is what we're working on, is that this is a double exponential curve that's basically just vertical, which means you're either too early or you're too late. But you don't want to be too late, and so I want all of you to be thinking about, and please watch the AI Dilemma, and I think advocate to your members of Congress that something has to happen to coordinate this race, otherwise it'll be out of control.
All right. Excellent point. Final question, again, as I was saying, changing gears from this important conversation about the perils or the potential perils. I just want to get both of your sense, Jan, if we scale things up even further, as you're saying, existing companies have the capacity to have the number of connections or parameters in the language of neural nets that rivals or exceeds that of the human brain. Do you anticipate that these AI systems will gain consciousness?
Okay, so first of all, the scenario that Tristan was describing, you just scale up and all of a sudden, an AI system can come up with a chemical weapon or something like that. As long as you train it with public data from the internet, that's impossible. Unless that data is already available on the internet, which means you can just get it by Googling, okay? You can get the recipe for sarin gas on Wikipedia. It doesn't make it easier for you.
It won't tell you how to make sarin gas on Wikipedia, I don't think.
No, but no LLM trained on public data will ever give you that because that information is just not available in public data. So that's not happening. This is not happening. It won't happen. And you can scale those LLM as much as you want. It will never happen. So, okay, so to answer your question, here's the thing. There is no question, absolutely no question, that at some point in the future, perhaps decades from now, we'll have AI systems that are as smart as humans in all the domains where humans are smart. And because humans are specialized, those systems might be specialized in different ways, but will be as smart as human, if not significantly smarter in all domains where humans are smart. Now, you say, oh my God, they're going to take over the world. No. Intelligence has nothing to do with the desire to dominate. Let's take humans. So humans have a desire to dominate. Some humans, not everybody. And it's not the smartest among us who want to dominate. We have examples of this on the international political scene, on a daily basis. There's probably some evolutionary reasons for this, right? If you are not that smart, you need the help from others, so you need to influence them. If you're smart, you can survive by yourself. That's the first point. Second point is, we are used to working with people who are smarter than us. I don't know about you, but I used to lead a research lab, and the only people I would hire were people who are smarter than me. It's actually great to work with people who are smarter than you. And our relationship with future AI assistants, which will help us in our daily lives, right? Project ourselves 10, 20 years from now, we'll have AI assistants that will help us in our daily lives. And they'll probably be smarter than us. But they will make us smarter. We will direct them. They will be subservient to us. It's not because they are smart that they want to dominate. The idea that you want to dominate is due to the fact that we are a social species. Because we're a social species, we need to be able to influence others, and that's where domination and submission comes from. We're a hierarchically organized social species. Evolution built that into us. It built that into chimpanzees, baboons, dogs, wolves. It didn't build this into orangutans. Orangutans have no desire to dominate anybody because they're not a social species, and they are almost as smart as we are. So that has nothing to do with intelligence. You can have a very intelligent system that has no desire to dominate at all. And so the way we will design those systems is to be smart. In other words, you give them a goal, they can solve that goal for you. But who determines the goal? We do. They will determine sub-goals. And the question of, the technical question of how you do this is not solved. This is something that we're imagining in the future, this objective-driven AI I was talking about before. But that's the future. Now, if we imagine that future, imagine that all of your interaction with the digital world and the world of information is through an AI agent. Those AI agents will be the repository of all human knowledge. It'd be kind of like Wikipedia you can talk to and can do inferences and everything, okay, but knows more than Wikipedia. This would be a common platform, sort of like the internet today. It has to be open. It cannot be proprietary. It's way too dangerous for this to be proprietary. That's your next movie. That's really the scary stuff. If you have a small number of West Coast companies controlling super intelligent AI systems, they can control everybody's opinion, culture, everything. Maybe the US government will go along with this. That's called regulatory capture. But I tell you, no other government in the world will find this acceptable. They don't want American culture to dominate theirs. They will have to build their own LLMs. So the only way to make this work is if you have basically open source, basic structure. This is one reason why Meta open sourced Llama 2, because it's a basic infrastructure. And before that, Meta released PyTorch. ChatGPT is built with PyTorch. It's a software system to build AI systems. So this will have to be open source. And the way you would train those systems will have to be crowdsourced, because you want those systems to be the repository of all human knowledge. And so all humans have to contribute to it. And they will not contribute to a proprietary system built by OpenAI or whoever, or by Meta. It will have to be open source. Despite, regardless of how dangerous you think this is, that's the way it has to go.
Sebastian, final word on any of the questions or topics that we've been talking about?
Yeah, I will answer your question about consciousness, but let me give final thoughts of a slightly different flavor. So, at the beginning of my career, I used to be envious of scientists from a century ago, were discovering quantum mechanics and discovering something really transformational, completely new, completely unexpected. And I feel like we're absolutely living through that period right now. I feel very, very lucky to exist and work right now on this topic. And I would never have expected that in my lifetime, there would be a system that would rise to the level that I would call it an artificial intelligence. Something really that looks like an intelligence, different from ours, but that looks like an intelligence. So this is really incredible. And I again, in my lifetime, I didn't think that I would ever be on stage talking about intelligence because this is such an ill-defined concept. So I'm not ready to talk about consciousness. I don't know if that will happen in my lifetime.
Please join me in thanking everybody for this fascinating conversation.